I'm Wil McCarthy, Futuresmith. I'm the author of Rich Man's Sky and other science fiction novels. You can find out more at futuresmith.com. So called hard science fiction is fiction where the science is correct, or at least sounds correct enough to satisfy a demanding audience. In this series, we'll explore how I've used simple calculations in a spreadsheet program to work out technical details for science fiction novels like Rich Man's Sky. Hi, welcome back. Today we're going to talk about explosions in space, primarily nuclear explosions, but the same equations apply to non-nuclear conventional explosions. Now, the thing to know about explosions in space is that they behave differently than explosions on Earth. Uh, when we think of an explosion, we typically think about a fireball. We think of a shock wave expanding out from the site of the explosion. We think maybe about a mushroom cloud as that fireball rises and pulls in dust and debris behind it, giving us that kind of classic mushroom shape. Um, None of these things occur in outer space. First of all, there's no gravity, but second and most importantly, there's no air. And the fireball and the shockwave in particular are features of the air and not of the explosion itself. Um, So, what we have instead is this kind of flashbulb event where the explosion emits a flash of energy that then expands outward in an expanding shell. Uh, and the amount of energy that's deposited drops off with the square of the distance. So, um, what we really want to know about an explosion is how much damage does an object receive at a radius r from the center of the explosion. So to calculate that, uh, we have the area of the object, which is measured in square meters, and then we have the delivered dose of radiation of energy, uh, which is measured in joules per square meter. And that's simply the total amount of energy released by the explosion divided by the surface area of the expanding shell when it's at radius r, which is 4 pi r squared, the surface area of a sphere. So the energy received by our object is equal to the total energy divided by 4 pi r squared times the area of the object in square meters. So it's a very simple equation, not very intimidating. We can use it to calculate different features of our explosions. So let's look at what that looks like. Um, Now, according to my research, we're going to use a backpack nuke, um, and apparently these can be as light as 24 kilograms. Um, so not a heavy bomb. And the minimum yield that you can have and still have it be a nuclear explosion is about 0.001 kilotons, so equivalent to about 1 ton of TNT. Uh, that's very small for a nuclear explosion, but still not anything you'd want to be close to. We will, for our purposes, model an explosion that's 0.01 kilotons or about 10 tons of TNT. So we're talking about a good sized truck bomb. Again, pretty small for a nuclear explosion, but still nothing you want to be close to. So we can calculate our yield in joules, which is simply this conversion factor here, conversion between kilotons and joules. A kiloton is a unit of energy, and so is a joule. So we look up on the internet this conversion factor here, and that tells us how many joules are released by our explosion. And the answer is 4 times 10 to the 10th joules are released by this particular explosion. So we can look at how it behaves at different ranges. Uh, if we go to a range of, say, 90 meters away from this explosion, we have ionizing radiation that's released by the bomb. And that ionizing radiation is this constant here times the yield of the bomb. This is the dose in Roentgens per kiloton times the number of kilotons divided by that 4 pi r squared that we talked about before. And what we find, uh, radiation dose is measured in Roentgens. Uh, then medically, we have Roentgens absorbed, uh, which is REMS. Uh, we can treat them as being equivalent for our purposes here. Now, at 400 REMS, that's what we call the LD50. That means it's got a 50-50 chance of being a lethal dose. Uh, at 1,000 REMS, it's the LD100, which means it's a 100% chance of being a lethal dose. So at a range of 90 meters, the dose that's emitted by this bomb or the dose that's received is 1,000 REMS per square meter. And a human is about a square meter in surface area, in frontal surface area. So we can say that at a range of 90 meters, this explosion is lethal to a human in terms of the ionizing radiation that's released. Now, that person might not die right away, but they definitely are going to die. But if we move farther out, let's say we move to 150 meters, then all of a sudden our radiation dose has dropped with the square of the distance. So now we're under that 400 rem LD50 dose, which means this person has a better than 50-50 chance of surviving just from the difference between 90 meters distance and 150 meters. So being farther away from the bomb definitely helps. Now, what about heat? We have heat that's measured in joules. Let's get that a little more visible. So once again, we have our delivered dose, our delivered energy is the total yield in joules divided by 4 pi r squared. And that tells us that at a range of 150 meters, we're delivering about 1.5 times 10 to the fifth, or about 100,000 joules. So I have some handy guides here telling us about different amounts of energy that are required to do different things. And basically, we have a certain amount that's required to boil a human, to vaporize a kilogram of iron, things like that. We can take these values and plot them here. And what's interesting there is we can then make a graph. And this graph tells us, let's scroll down a little bit. This graph tells us something interesting, that this dotted line here is the line where a human gets vaporized. So what this says is very close to the explosion, a human will be vaporized. But as you move even 50 meters away, that's not a risk anymore. Now, second-degree burns to exposed human tissue, that's a risk out to about 150 meters. And beyond 150 meters, you're no longer getting those second-degree burns. What's interesting, this gray line is the ionizing radiation. Our LD50 dose is this line here, and our LD100 dose is this line here. They're actually quite close together. And what this tells us is that at a range of 300 meters, we have about a 50-50 chance of being killed by this explosion due to radiation, even though we're not even getting second-degree burns from it, from heat. This tells us that a nuclear explosion in space is much more of a problem for ionizing radiation than it is for heat. And so this is not how nuclear weapons are typically portrayed in science fiction movies. And it's good to get these details right. So that's that's how we calculate nuclear explosions in space. Now, if you want to calculate a conventional explosion, it's very simple. Just delete the ionizing radiation curve here. We don't have one. And instead of having our yield in kilotons be from a 24 kilogram device, our yield in kilotons is from a 0.01 kiloton device. So again, 10,000 pounds of TNT. That'd be a large, if you have a missile that's striking with a warhead, that'd be a very large warhead for a missile. So this is why nuclear warheads are, backpack nuke warheads are more convenient. But anyway, this is how we calculate the effects of an explosion in space. If you have any questions, feel free to email me. Otherwise, please like, follow, and share. And we will see you next time.